Hello and welcome to another video. So in this video, we will see the basics of controllers. So here, in an open loop system, we have a plant G of S and an input R of S and output C of S. So there is no feedback or a controller here. We just give some random settings to the input and it applies on the plant and an output is generated based on it. An example of this is an electric iron which we use at home. So we change the setting of the iron and we iron the fabric. So if the iron is very hot, we manually change the temperature. So there is no sensor to sense what is the temperature of the iron, and accordingly it feedbacks and automatically adjusts the settings. There is nothing like that. We manually adjust that setting of the iron. So here sometimes see our set temperature is 50 degrees Celsius. What we require is 50 degrees Celsius, the set point. But right now the setting is such that the temperature rises and it settles at some other value, say 20 degrees Celsius. And then we understand that the temperature is not enough to iron the fabric. Then we change the setting and we increase, this temperature is increased manually. So that is an open loop system. But in automatic control, we use another controller in between this plant and the set point, so that this controller modifies the plant, will affect this plant and will reach our desired temperature automatically. So suppose in a vehicle speed control system, in an automatic vehicle speed control system, the plant is the car or the vehicle. Now the desired speed of the vehicle, say 50 kilometer per hour, and the output right now is 25 kilometer per hour. We sense this current speed by using a speedometer, and it is fed back to this comparator. So the comparator compares this 50 and this 25. So there is a difference. So that difference is called error. So this difference, this error comes here, and it is given as an input to the controller. So the controller will adjust, will give a signal to the car. Here in this case, it will push the accelerometer pedal so that the speed of the car is increased. So this accelerometer, when the pedal of the accelerator is pressed, this motor runs and at a higher speed, and that car runs at a higher speed. Now this part is what makes it a closed loop system. The sensor as well as this control. So in an automatic control, we have this two setup, this sensor as well as this controller part. Now our goal is to reduce this error between the output and the set point. So this is the set point and this is the actual response, the output. So the output gradually increases and reaches this set point. So it is not that from 25 it directly goes to 50. It when we press the accelerometer, it increases from 25 to 30, 30 to 35, 35 to 40, and then it reaches 50 kilometer per hour. So today we will discuss what are the basic types of this controllers, GC of S. So the basic controller that we will discuss here is, the first controller is proportional controller. So the proportional, as the name suggests, it is proportional to the error. So the controller output P will be proportional value to the error, is directly proportional. And this proportionality constant is Kc. So the transfer function of this proportional controller, the relation between the output P of S and the input E of S is Kc. So it is just a simple gain. So the value can be 1, the value can be 0.5, the value can be 2. So any constant value. So the relation between the error and the output of the controller is this part, the signal that is given to the plant. So the output of the controller and the error is directly proportional. So suppose the error is say 25 and the gain is Kc is 1, then the output of the controller will be 25. So it is just multiplied by a simple gain Kc. Kc can be any value. So based on the value of Kc, the slope can differ. Sometimes it can be like this. Sometimes it can be like this. So whatever be the slope, the important part is that this is just a constant. So the relation between the error and the proportional output is just a constant. Now this has only one adjustable parameter. This type of controller has only one adjustable parameter, the gain. So we can change only the gain value. But this has a drawback that the output of the system will have some residual error. So it will not reach the exact set point. There will be some error. So if that error is within the tolerance of the user, then it is better to go for this proportional controller because it is a very simple controller. So we will move on to the next type of controller. The next type of controller is proportional integral controller. So when we require this track the set point exactly without any residual error, then we go for this kind of proportional integral controller. So the proportional I have seen earlier, this part, it is proportional to the error. So it is just with a proportionality constant Kc, it is proportional to the error. And the second part is that we, along with that, we add this integral term. So here we have two adjustable parameter. One is this gain Kc, another is this tau I. Tau I is the integral time. So we have two adjustable parameter here. Now, what happens for a proportional integral controller? The transfer function looks like this, Kc into 1 plus 1 by tau is. Whenever suppose you have a step change in the error. So here, if there is some sudden change in the error, R of S is at 50, and earlier it was tracking, and then sudden change in the error. Suppose this 50 is changed to some 60. So there is some sudden difference. Here it is 50, and what it already was tracking feedback was 50. Now from 60 to 50, there is a difference of 10. Now there is some sudden change in the error. So what happens? What is the response of the proportional controller? So earlier it will until this step change happened, it was some predetermined value, and whenever there is some sudden change, this there is a response from the proportional controller. This output P of S will be something like this. It will have sudden rise, and the rise is equivalent to the Kc. That is due to the first part. And there is some rise in Kc, and then it gradually integrates, it gradually rises. So so this integral part, as error is prolonged, prolonged for a lot of time, it will integrate it. It will add up all these values. So, as we add up all these values, the proportional output will also increase. So a more and more effort will be given for P of S, so that it forces this plant to track the output. So whenever there is even a small error, it will add up. It will, the controller output P of S will add up, and it will increase more and more effort so that the control will be tracking exactly the set point. So R of S and C of S will reach at the exact value. So that is how this works. We will discuss both these and few other controllers like proportional derivative controller, proportional integral derivative controller with examples in another video. Thank you.